question 63, unique passes number 2. You are given n by n integer array grid. There is a robot initially located at top left corner here, and the robot tries to move to the bottom right corner here, and it can go only to the right and down. And there might be obstacles along the way, and in the grid, as you see here, the obstacles are shown with 1, and the like cells that there is no obstacle are shown with 0. So we should return the number of unique passes that we can take the robot from this corner to the bottom right corner. To solve this problem, we are going to traverse the grid, and we are going to traverse it like a binary search tree. So we start from this corner, this cell at index 0, 0, and we go to the right and we go to the bottom, and at every single point we go to the right and we go to the bottom, and we call this function recursively until we find all the possible passes. So let's see how we can do that. We are going to have a recursive function, and I'm going to call it like DFS, and I'm going to pass I and J. I and J are the indices of the row and columns. So I'm going to say if I wanted to make sure that they are like in the like within the range. So within the range, we need to make sure that I is smaller than if I is smaller than 0, or if I is bigger than m minus 1. So let me define m is going to be length of the obstacle grid, and n is going to be the length of the obstacle grid 0. Okay, so we make sure that if I is smaller than 0, or if I is bigger than m, or if j is smaller than 0, or if j is bigger than n minus n, or if we have an obstacle. So if the obstacle grid at index I and j, all right, if it is equal to 1, what are we going to do? We are going to return 0. And what if and if it is like that, we are going to return 0, and we get like to the rest of the stack for the recursive function. And if what I'm going to do here, I'm going to say if I is equal to m minus 1 and j is equal to n minus 1, which means we are at this point at the bottom right corner, I'm going to return 1. The reason that I'm returning 1 here, it means we have found a path, a unique path to get to this cell, and we are going to return 1. And what I'm going to do with this 1, I'm going to have a count here that starts from 0, and when I call this function for the right cell and bottom cell recursively, I'm going to check if I need to like add 1 to the count, which means we are at the right spot, or we just pass that. So I'm going to say count plus equal, I'm going to call this function recursively. For the right, it's going to be I j plus 1, and for the left, it's going to be dfs I plus the bottom one is going to be I plus 1 and j, right? And at the end, we are going to return count, right? And let's say when we are done with this helper function, we are going to return dfs at index 0, 0. We start from 0 here, and we call this function recursively. I'll go through an example later, but I think we have no error, and let's run the code and see if it works fine. It seems fine to me. Let's see. There we go. It's working fine. And the time complexity for this is going to be n by m, because we need to traverse the whole grid. and space complexity is and as well because we are using a stack for the recursive function. What I'm going to add here is for like Python functions that they call it themselves like recursively, we can use LRU. What is LRU? LRU is least recently used cache strategy. So I'm going to add the LRU decorator here, and I'm going to say max size is equal to 16. The reason that I'm doing that, the LRU, this decorator is from Python Func tool, and it's a decorator that is give us the ability to cache the result of our function using LRU. And it's a good technique to use caching, especially for these cases that we are calling a function recursively. And that's about it. Thank you.